Okay, let's just introduce enthalpy of reaction. So chemical reactions are either going to release energy or take energy in as a total. So for example here, we can see this a couple different ways. We can see the thermochemical equation, which is a chemical equation with therm, heat added to it. Keep in mind, this positive is not a mathematical sense. It just means and. Just like there's not a negative aluminum oxide, it's just and. So this is iron and aluminum oxide, and energy is produced. When energy is produced, the change in enthalpy is negative. Oops, it looks like I inverted my numbers here. Whoops. Oh well. So the idea is that the energy being released is going to be given off as a product. I often think of with energy being produced, it's being released to the surroundings. That's how we know it's there. If we had this value on the other side, it'd be endothermic, and that value would be positive. One of the things I wanted to show you here, though, is that the amount of energy is related to the amount of moles from our chemical equation. So for every 1 mole of aluminum, it would be half as much. 4 moles would be 4 times as much, or I should say twice as what we had there. I gave another example, butane, like we find in lighters. We've got our thermochemical equation, our chemical equation with enthalpy on the outside, and that 2 moles of butane is for this amount. Same idea, 13 moles of oxygen, same amount, 10 moles of water, same amount. And again, it doesn't matter which one is on top and bottom. These are conversion factors that can be used when we do some stoichiometric calculations. Like this in action. So if I was trying to vaporize 175 grams of water from 20.4 to the reaction, what would I need to have here? So if I'm using this idea of aluminum, I first need to find out how many joules it takes in order to get there. So if I take my mass of water times my specific heat, temperature change, this would get it to boiling, so many joules. Then to vaporize it, so many more joules. I added those together and turned those into kilojoules. Then I can use that kilojoules amount, use our enthalpy of, what do we call it? Reaction. Keep forgetting that. Enthalpy of reaction to determine my number of moles to grams, and it would see that 28.8 grams of aluminum reacting with the other iron oxide would release enough heat to heat my water to all gas. That's the way that this can be powerful. We can see that this part here, we're utilizing it as a conversion factor. So taking our previous chemical reaction to the next level, let's say it took so many kilojoules to light a fire using a lighter. What would be the change in pressure in a lighter of 17 milliliters in a temperature of 18 degrees? So my amount of energy that was needed, again, kilojoules, I can use my relationship here to see so many moles of butane would be used up to produce this much energy. So therefore the fraction of it would be a fraction of moles. I can then take that moles amount, put it into my PV equals nRT, and see that there would be a small pressure change based upon this here. And you might say, well, isn't that the final pressure? No, because this is amount the moles that change. So this is the amount of moles that changed. Therefore, this would be my pressure change. Again, this has a lot of variety of adding to our toolbox of what we can do with chemistry. And again, on AP, they might mix these up. They might put them together. They might have them individual. But the idea is that we can use our enthalpy of reaction just like a conversion factor. And remember that it goes with the coefficients of the substances provided. Come in with your questions, and I'll catch you on the flip side. Ugh.